The title of this paper is Delamination Analysis of a Fixed-Ended Multilayered Beam under Twisted Support. The application of multilayered materials and structures increases in various sectors of engineering. One of the disadvantages of multilayered structures is the delamination. This paper studies peculiarities of the delamination behavior of a fixed-ended multilayered load-carrying beam structure under twisted support. The layers of the beam are of different materials and may have different thickness. Besides, the layers are inhomogeneous along the beam length. The cross-section of the beam is a rectangle. Both ends of the beam under consideration are fixed. Therefore, the beam represents statically indeterminate structure. No external loading is applied on the beam. However, the left-hand support of the beam is twisted. This induces shear stresses and strains in the statically indeterminate beam, which leads to delamination. The strain energy release rate for the delamination crack is derived. For this purpose, the strain energy in the beam generated by the twisted support is determined and then differentiated with respect to the delamination area. The compliance of the beam under twisted support is analyzed to perform a verification of the solution of the strain energy release rate. A parametric investigation is carried out in order to clarify the effects of a variety of factors like magnitude of the angle of support twist, beam geometry, configuration of layers, distribution of properties of layers along the beam length on the delamination behavior. Since the layers of the beam are inhomogeneous along the beam length, the shear modulus changes smoothly. This change is defined by formula number 1. The quantities x, L, and n are defined in figure number 1. The quantities G, J, L, and F, J represent the volume of Gj at the left end of the beam and the parameter of the change of the shear modulus. In order to determine the strain energy release rate, the static indeterminacy has to be resolved first. This is done via equation number 4. In this equation, U is the strain energy accumulated in the beam, Tb1 is the torsion moment in the left end of the beam, the strain energy is given by using equations from number 5 to number 8. The quantities A1 and A2 are defined in figure number 1. N1 is the layer number in the lower crack arm. Equations number 9, 10 and 11 define the specific strain energies. In these equations, tau ij and gamma ij are the shear stress and strain induced by the support twisting. The specific strain energies are defined by shear stresses by using formulas from number 12 to number 14. After resolving the static indeterminacy, the strain energy release rate is obtained from the strain energy via formula number 15. Actually, formula number 15 is aimed for calculating the strain energy release rate at increase of delamination in the delamination tip in cross-section B2 of the beam. The strain energy release rate at increase of delamination in the delamination tip in cross-section B4 of the beam is derived by applying formula number 16. Formulas number 17 and 18 derived by the compliance method are used here for checkup of the strain energy release rate determined via formulas number 15 and 16. The compliance C is given by formula number 19. The findings from equations number 17 and 18 confirm the strain energy release rate obtained from formulas number 15 and 16. It is studied how the strain energy release rate in normalized form varies as a result of change of different parameters. This is done in order to see the effects of these parameters on the delamination in fixed-ended beams under twisted support. The diagrams shown in figure number 2 represent variation of the strain energy release rate induced by change of parameter F1 for different values of phi d1. The rise of the angle of support twist causes significant growth of the strain energy release rate. The reduction of the strain energy release rate that is generated from increase of F1 is a consequence of growth of the shear modulus in layer 1 of the beam. Figure number 3 shows variation of the strain energy release rate that is caused by two factors, N1 and G2L to G1L ratio. The variation observed is characterized by reduction of the strain energy release rate with growth of both N1 and G2L to G1L ratio. The variation of the strain energy release rate generated by growth of H to B ratio is presented by graphs shown in figure number 4. The graphs 1 and 2 in figure number 4 correspond respectively to increase of delamination in the delamination tips situated in cross sections B2 and B4 of the beam structure. There is a qualitative similarity between the two graphs in figure number 4. Another important finding from figure number 4 is that the strain energy release rate for increase of delamination in cross section B2 of the beam is significantly higher than that for increase of delamination located in cross section B4 of the beam. This is explained by the rise of the volus of the shear moduli of the inhomogeneous layers from the left end towards the right end of the beam. Thank you for your attention.